Okay, so welcome to the final hottest talk of 2021. The next talks will resume in January with our event for junior researchers on January 13th. So this week's speaker is Taichi Uemura from Stockholm University, and his title is Infinity Type Theories and Internal Language Conjectures. Please go ahead.
Thank you. So thank you for inviting me and organizing this nice electronic seminar. Yes, so today I want to talk about higher dimensional generalization of type theories, which we call infinity type theories. Before that, this is joint work with Kim Guen. Anyway. So we are I'm talking about infinity type theories, and the motivation is to give a unified formulation of internal language conjectures and give a proof of such internal language conjectures. And for now, we have a proof of a particular internal language conjecture given by Kapulkin and Lumsdaine. That is a internal language conjecture for finitely complete infinity categories. Anyway, so let me explain some backgrounds, namely explain internal language conjecture. So one of the goals of homotopy type theory is like this. So dependent type theory with intensional identity types, dependent function types, invariant universes, and higher indicative types gives internal languages for what should be called elementary infinity toposes. Okay. But this is a really difficult problem, I guess, because the type theory is really a complex type system, and also we have not known what the correct notion of elementary infinity toposes. So it is nice to begin with a much more simpler version of that conjecture. I think the simplest one is like this. I mean, dependent type theory with intensional identity types gives the internal languages for finitely complete infinity categories. Okay. And the first step is to make a precise formulation of this conjecture. And this was given by Kapulkin and Lumsdaine. They first constructed some functor between some infinity categories. The domain is one category of models of dependent type theory with intensional identity types, which I really don't like this. So this I stands for intensional type theory. Yeah. And the other side is infinity category of small infinity categories with finite limits. So first of all, they constructed such a functor, and then conjectures that this functor induces an equivalence between infinity categories. The right-hand side is the same, the infinity category of finitely complete infinity categories. The left-hand side is a localization of the one category. That is an infinity category obtained from these models of I by adjoining formula inverses of certain morphisms. Okay, so all right, and so the basic approach to this conjecture is to analyze this functor, of course, and this is constructed by several steps. First of all, well, from models of dependent type theory, the intensional identity types, we can form some categorical structure called vibration categories. This is given by these people. And the fundamental point, the important point is identity types give a kind of weak factorization system, and this is sort of a kind of homotopical algebra-like things. And then Shimiro proved that the category of vibration categories are equivalent up to localization to the infinity category of finitely complete infinity categories. And one more step is was given by Kapulkin and Shimiro. They proved that vibration categories are equivalent to so-called tribes of under JR. So tribes are slightly closer to the syntactic presentation of type theory than vibration categories. So it's nice. Okay. So this is an existing approach to the internal language conjecture. But today we we seek a totally different path from this decomposition. We introduce some intermediate infinity categories of models of infinity type theories, and mainly working on infinity categories rather than one categorical models of type theory. Okay. So why different approach? Yeah, because the existing approach is almost successful, I guess, but still the first step is slightly involved. So, yeah. But the problem is that
Sorry, I have a question.
Okay.
Can you go back, please?
Yes.
Can you go back one slide? There are various different kinds of equivalences displayed here. I'm just wondering what they are. For example, 2 is probably an infinity category. What about 1? Is that an equivalence of 1 categories?
1 is no, they are not. I think not. I think they are not equivalent.
Right, I think
as a 1 category.
And what about 3? What about 3? What about 3?
3 is not an equivalence of 1 categories, but equivalence between the localizations of them. Okay, so equivalence of infinity categories.
Okay.
Okay. Yes.
Good.
Okay, so the problem of this 1 categorical approach is that the intermediate 1 categories, namely the categories of tribes and the category of vibration categories, are not so easy to work with, to my impression. For example, well, in the category of models of dependent type theory, we can relatively easily compute homotopy co-limits. And on the other hand, in the category of vibration categories, homotopy limits are easy to compute, but I'm not sure about homotopy co-limits of vibration categories. So there is already a kind of mismatch of homotopical structures, right? And even worse, in the category of tribes, we are not sure if how to compute homotopy limits and homotopy co-limits. And this is main difficulty of the Kapulkin and Shimiro's result. And also, it seems to be also it is unclear how to generalize this approach. And if we extend the type theory by pi types, inductive types, and so on, then how to, well, what is the correct notion of vibration category with, say, natural number objects? I think it's not so obvious. All right. And also, the coherence problem is not solved at once. Let me see. So the final, the last equivalence of the vibration categories and the finitely complete infinity categories is regarded as a kind of strictification, right? Yeah, most of yeah, because it means that finitely complete infinity categories are presented by one category, some sort of one categories. But in vibration category, Pruvacs still up to isomorphism, and this is also still a coherence problem to be solved. So I think it's not. Maybe it is okay, but well, it might be problem. So yeah, for that reason we seek another approach. So we introduce a notion of infinity type theories, which is analogous to ordinary type theories. So we some models of infinity type theories make sense, and the models of infinity type theory form some infinity categories. And so some technical advantage of this approach is that these infinity categories are all presentable infinity categories, which is very nice. For example, they have all limits and co-limits, and also some adjoint functor theorems are available. So these functors are actually just a formal consequence of adjoint functor theorems. And also, another nice thing is that all but the last step are formulated within the language of infinity type theories. So these three categories, these three infinity categories are all infinity categories of models of some infinity type theories. So in that sense, I think it is easy to generalize. If we add type theory, if we add to type theory some other type constructors, pi types, inductive types, universes, then we consider analogous infinity type theories with those type constructors. Then we can construct similar functors. And also the coherence problem arises only at the first step, namely between the type theory and infinity type theory. So because the rest is are in the infinity categorical setting, so there's no gap between the levels of equality, right? So the first step is the only place where the coherence problem comes in. Okay. So the goal of this talk is to prove the following. First of all, our functors gives the same functor considered by Kapulkin and Lumsdaine. And then it induces an equivalence between these infinity categories. Okay. So this is the contents of my talk. So we first introduce infinite type theories and give a formulation of internal language conjectures, and then discuss coherence problems. Okay, so what is infinity type theory? Very informally, it is on higher dimensional generalization of type theories. What does it mean? So informally, it looks like a type theory with proof-relevant version of a judgmental equality. So, if we replace judgmental equality of type theory by some content-free equality, we get some type theory with proof-relevant equality. So if we make judgmental equality proof-relevant, then the equality between, well, equality between equalities and so on makes sense. So it is natural to consider higher dimensional equalities between equalities. So it looks like some infinity thing. This may be compared to some type theory with explicit conversion like this. Okay, but this is really informal explanation, and this is not a quite definition of infinity type theory. If we want to give such a proof-relevant judgmental equality, we essentially have to write down all the coherence laws of infinity one category algebraically. So we don't know how what is a good way to write down all the inference rules for this kind of judgmental equality. So instead, we define an infinity type theory slightly more infinity categorically. Precisely infinity categorical generalization of categories with representer maps. So let us remind, or let me explain what is it. I begin with a definition of exponential morphisms. So recall that a morphism in a category with finite limits is exponential if the pullback along it has a right adjoint, and this right adjoint is called push forward, or it may be also called a dependent function. So for type theoretically, this push forward corresponds to pi types. Okay, and category with the representer maps, CWR in short, consists of first of all category, for which I require it having finite limits, and also a class of exponential morphism in C, and they require some stability conditions like stable stability and pullback and so on. And the morphisms in R are called representative maps. Okay, so it is essentially a category with finite limits and a class of exponential morphisms. And the motivating example is a pre-shift category. So in a pre-shift category, a map F from B to A is representable if for any object in the base category and the section of the pre-shift in the bottom. Then if we take the pullback, then it is representable. The representing object, which I denote by x dot a, is called the context extension along F. So, and my definition of a type theory is just a CWR. Okay. So the quick intuition is some intuitions are say type theories should be first of all essentially algebraic theory which corresponds to category with finite limits. I mean, essentially algebraic theories correspond to categories with finite limits. But also type theories are involved with variable binding, right? And variable bindings are, well, for example, in logical frameworks, variable binding is expressed by dependent function types. So in that sense, push forward along representative maps are used for variable binding. Yeah, so these are rough intuition for why type theory categories with representative maps. Okay, then we can define a model of a type theory in the functorial style. Namely, a model of type theory consists of base category with a final object and a morphism of CWRs, which are just a functor preserving all the structures up to isomorphism. Okay. So for example, examples of type theories are, well, kind of given by some presentations. So if we look at the definition of a category with representative maps, it is essentially algebraic in to one categorical sense. Okay. Because finite limits are defined by junctions and push forwards are defined by junctions. So it's essentially algebraic. So in that sense, we can define type theories by kind of generators and relations. So for example, we can define a type theory D, which is presented by two objects U and E and a representative map between them. So what does it mean? So we can concretely describe models of D. So it consists of a space category M star and a representative map, and a morphism from D to a precise category. But because this is presented by this data, such a morphism is completely determined by the values at the generators. So therefore, a model of D is consists of a base category and just a representative map of perceived of the base category. And this is nothing but equivalent to a natural model or category with families. So we can recover classical notion of standard notion of models of type theories. Okay. So we consider extending this type theory. So this D corresponds to the type theory without any type constructors. So we extend it by joining some type constructors. For example, let I be the intensional type theory. So we add intensional identity types, which are defined by some, first of all, commutative square. So ID is the formation rule, and the reflexivity is the introduction rule. And the commutativity means that the type of reflexivity is ID of A. The type of reflexivity is just A equal A. And we also add a path induction operator, which is slightly complicated, but we can define it as a morphism and equation representing the computation rule. Okay. And for convenience, we always assume unit type and sigma types. They are also defined in the morphisms and equations. Okay. One more definition. so a model of type theory in my sense, or even or it is also true for categories with families and natural models. These kinds of models of type theory contain a lot of objects in the base category. But we are mostly interested in the more restricted class of models of type theory. Namely, if we build a model of type theory out of a syntax of type theory, such a syntactic model has a special property that every object in the base category looks like is a context. And we formulate the notion of context like this. So for the class of contextual objects is inductively defined. Namely, final objects are contextual, and context extension of contextual object is also a contextual. And then we say a model is contextual if every object in the base category is contextual. And then we define the full subcategory of contextual models. So for example, if the contextual categories with families or contextual natural models are equivalent to what are called contextual categories of Cartmel. And it is known that contextual categories are equivalent to generalized algebraic theories. So in that sense, contextual models precisely correspond to syntactically represented theories. Okay. We have a theorem. The category of contextual models of T is in fact equivalent to the category of functors from T to set, preserving finite limits. Okay. And yeah, and this equivalence is really can be concretely described. Just take the evaluation at the final object in the base category, then we get some functor from T to set. So as a corollary, so from the definition of contextual objects, the left-hand side is slightly complicated. It is not, so for example, it is not this, sorry. At first sight, it is not, we are not sure the category of contextual models is essentially algebraic. But the right-hand side is by definition essentially algebraic. So which means that in particular, for any morphism between type theories, we have junctions between the categories of contextual models. Okay. So what we have done, so yeah, we defined the type theory as a category with representable maps and defined the model of type theory in a functorial style and defined the contextual models. And so that any morphism between type theories induces a junction between contextual models. So all of them are kind of purely categorical. So it is straightforward to generalize this story to the infinity categorical context. Okay. So So we can define a notion of infinity category with the presentable maps in a straightforward way. Then we define an infinity type theory to be an infinity CWR. And for convenience, we define an N-type theory to be an infinity type theory whose underlying infinity category is an N category. So in that sense, ordinary type theories are one type theories. And then we can also define a model of infinity type theory. But in this case, instead of the set valued precisions, we consider space valued precisions. Okay. Then we also have a similar representation theorem of contextual models, namely the infinity category of contextual models of T is equivalent to the infinity category of functors from T to spaces, preserving finite limits. Okay. Any questions at this moment? I don't know. Okay, so we defined infinity type theories and their contextual models. So we can now formulate internal language conjectures in a general way. So we start from some one type theory T. Then we can ask some, then we consider some internal language conjecture for this one type theory. So first step is to define an analogous infinity type theory T infinity, which will be essentially the same as T, but defined as an infinity type theory. Or in other words, this T infinity is an infinity type theory such that T is one truncation of T infinity, or something like this. And then we define another infinity type theory. We write T infinity X, which is obtained from, sorry, this is T infinity. So T infinity X is obtained from T infinity by adjoining some extensionality principles. And then we have a span like of infinity type theories. The left side is a kind of truncation map. And the right hand side is a kind of localization map, which induces functors from contextual models of T to contextual models of T infinity X by first bring back and then pushing out. Okay. So if we have correctly define T infinity and T infinity X, we obtain a functor from contextual models of T to contextual models of T infinity X for free. Then the task is that first of all, we want to determine some concrete infinity category of infinity categories with some structure, which is to be equivalent to this last one. And prove the localization of this composite. This composite of functors induces equivalence between the localizations. then we are done, right? So if we proved these things, then we can say that the T is a internal language for the infinity category X or something like that. Okay, so let me see an example, the motivating example. So we consider an infinity version of the intensional type theory. So we can define infinity type theory I infinity presented by the same data as I. That is, it is generated by first of all representative map and intensional identity types. But in this case, this is to be a homotopy commutative square. So it consists of a map ID and a ref, and also the homotopy filling this square is also part of data. And also path induction operator is to be a morphism and a homotopy expressing the computation rule. And also we add some morphisms and homotopies for unit type and sigma types. Okay. So almost by definition, the intensional one type theory is one truncation of the intensional infinity type theory. More precisely, this I is the initial one type theory equipped with a morphism from I infinity. Okay. And also we can observe that the Pruvac functor is an embedding. Namely, this type is free faithful, and also we can characterize its essential image. Namely, the essential image consists of those models of I infinity, such that those perceives are zero truncated, or in other words, those perceives are set valued. Okay. Then, so we have defined the intensional infinity type theory. So then next we define extensional infinity type theory. So which we write E infinity, because it stands for extensional type theory. So this is obtained from I infinity by the following operations. First of all, we make the identity types extensional. What does it? Which means that we make this square Pruvac. Or in other words, or alternatively, we can invert the induced morphism. We can make the induced morphism from E to the, I don't know, E to the Pruvac invertible. And we also make this generating representative map to be univariant. We'll explain later. And then by definition, well, because E infinity is obtained from I infinity by this operation, we have an obvious morphism from I infinity to E infinity. Okay. Why not the infinity is the initial infinity type theory. initial infinity type theory equipped with these morphisms such that the square is Pruvac and this representative map is invariant. So what is invariance? The invariant morphisms are already defined in the infinity categorical setting. First of all, we observe that for any representative map in an infinity CWR, we can construct the object equiview, which classifies equivalences between fibers of this map. This is constructible because U is exponential. So we can construct a kind of function spaces, and then we can form an object of bi-invertible maps. Then that is gives and then that classifies equivalences between fibers of U. Then in particular, we have a section of this equiview over the diagonal corresponding to the identity. And then representative map U is univariant. Representative map U is invariant if this canonical morphism is an equivalence. Okay. So example is kind of classifying morphisms. So suppose that infinity CWRC has a generic representative map in the sense that any representative map is a pullback of the generic one in a unique way. I mean, unique way up to constructive choice. Then such a generic representative map must be univariant. So for example, well, any precise category, any precise infinity category has a generic representative map. This is essentially because precise categories is an infinity topos, but more concretely, when the base category D has finite limits, for example, then the generic representative map is constructible from the usual codomain fibration. Okay. So in the case of D has finite limits, we can concretely construct the generic representative map. Okay, so we can now make the definition of infinity precise. So making D to be univariant, making D to be univariant means that we invert the canonical morphism. Okay. This notion may be compared to some of work of Raphael Bouquet. I remember in the in his talk here he was talking about some form of univariance. But his presentation was more syntactic, but I guess we are essentially doing the same thing. Okay. All right, so we defined an extensional infinity type theory, and which it is natural to expect that this infinity is internal languages for finitely complete infinity categories. And this is indeed true. More precisely, we have a forgettable functor from models of infinity to infinity categories by taking the base infinity category. And in fact, this base infinity category has finite limits and induces this equivalence. And the inverse construction is also easy. Just given finitely complete infinity categories, we take the generic representative map in this precise infinity category. Then this is part of contextual models of infinity. And yeah, we are done. And we may, it might be worth noting that the proof is more straightforward than the one categorical case of Clay-Lambert and Riviere, because we don't, in the infinity categorical setting, we don't have to deal with any coherence problem. Okay, so then we have internal language. We reformulated the internal language conjecture for finitely complete infinity categories. And we constructed these functors and conjecture that this induces equivalence between the localizations. But the construction of these functors also are easily generalized. And we get a family of internal language conjectures very easily. So if we add pi types with function extensionality, then we also construct analogous infinity type theory with pi types. And then we get extensional infinity type theory with pi types, and which naturally corresponds to locally contingent cross infinity categories. And if we also add natural numbers type, then we will do the same thing, and we'll get some. And the last one will correspond to locally contingent cross infinity categories with a natural number object. We can also consider universes. So if we start from type theory with countable chain of univariant universes, then we will get some infinity categorical structures. So because the countable chain of universes is a kind of explicit structure of the type theory, at the end we will get some notion of infinity LCCs, infinity locally contingent cross infinity category with countable chain of universes with as part of structure. Not merely the existence of universes, but we will get some notion of infinity categories with universes. I'm not sure if this can be used as definition of elementary infinity toposes, but maybe it's something to think about. And also we may consider higher inductive types. So for example, if we add the unit circle, we will get some locally Cartesian cross infinity categories with unit circle defined as a sum colimits. Okay. Okay, so we back to the internal language conjectures for finitely complete infinity categories. So we prove that these composite indices are equivalence between the localizations. And the functor coincides with Kapulkin and Lumsdaine's. So how to prove? And the idea is that, well, if we prove that this composite preserves some homotopy colimits, then the rest is not so hard. So to be precise, first of all, Kapulkin and Lumsdaine already showed that the models of intensional type theory is equipped with the structure of a co-fibration category, which in particular means that certain colimits in the models are already homotopy colimits. And then we want to prove that the tau star preserves those colimits, and then automatically the composites also preserves colimits because gamma shrink is a left adjoint. And then, so if we preserve these, if we prove that the functor preserves those colimits, then by the result of Szysinski, it is enough to check a couple of conditions called the left approximation property. I think it is relatively easy to verify. And then the last assertion, right. Last assertion, namely this functor is the same as Kapulkin and Lumsdaine's, is verified by that both functors have the same universal property. Okay. So in this, so in our proof, the second step, namely proving that tau star preserves some colimits, is the most difficult part. Okay. And we will, yeah, and today in the rest of the talk, I will discuss how to prove this part. All right, so first of all, okay, we remind the Kapulkin and Lumsdaine's result that the category of models of type theory, intensional type theory is equipped with the structure of co-fibration category, and it is actually a part of combinatorial left same model structure. So it has actually more rich structure. And but the important thing is that the co-fibration is defined as a retract of an extension by types and terms, but no equations. And our model is called cofibrant if the map from initial object to M is a cofibration. So essentially a cofibrant object is a model freely generated by types and terms, but without any equation. Okay. And this definition also works for models of I infinity, just by analog. And then the key lemma in our proof is like this. Any cofibrant object of models of I infinity actually belongs to the models of I. This is a kind of coherence theorem. So cofibrant object is almost a free model of I infinity. So this theorem asserts that in a free model of I infinity, any diagram of homotopies must commute. Okay. Because models of I is just a model of I infinity, which is set valued or zero truncated. So models of I should have only trivial homotopies. So this theorem asserts that in any free model of I infinity, all the homotopies are trivial. Okay. And as I said, this is the only place where the coherence problem comes in. And if we prove this theorem, it is straightforward to see that the inclusion preserves some colimits, namely initial objects and push-outs of cofibrations. Okay. So we quickly discuss how to prove coherence problem. And classical approach for coherence problem is a split replacement, which is given by Martin Hoffman. So the idea is given a model of I infinity, we want to find its split replacement, which is to be a model of I and equipped with a trivial fibration for splitting of M to the given M. So if we have such a split replacement, it is immediate that this theorem is immediate, because if we start from a cofibrant model of I infinity, then it becomes a retract of the split replacement. Then yeah, by a retract arguments, M itself is also belongs to the category of models of I. Okay. There can be also another approach, which is a syntactic in some sense. Although we don't have syntax for infinity type theories anyway. We may use some rewriting or some normalization arguments like this, but we have not yet done these approaches. So what we have done is to construct a split replacement for models by infinity. So recall that a model of I infinity consists of a base infinity category and a representative map of precipes and some maps and homotopies. So the idea is like this. So first of all, we present this infinity topos of precipes by some nice model category X. Then this representable map is represented by some universe in this model category. So anyway, we have some map in one category X. Then we can use a kind of so-called universe method of Voevodsky to obtain a contextual natural model of contextual natural model. But this model is just a natural model without any type constructors. So we also have to lift the identity structure of the given model to this split replacement. Okay. So thanks to Sharman's result, we can choose a very good model category X, which is called type theoretic model topos. So for now, we just remark that all the cofibrations in type theoretical model topos are precisely the monomorphisms. Okay. And then we can choose some fibration between vibrant object in the model category X, which is sent to the representer map. And then we define a contextual natural model like this. So first of all, we take the Yoneda embedding. Then we get some natural model, and then restrict this model, restrict the base category to the full subcategory spanned by the contextual objects. Okay. More precisely, we can take the base category to be a full subcategory of the X, and these perceives are defined by the homosets. Okay. So we have some natural model anyway. Then we construct the lifting identity type structures. So the situation is like this. We have a vibration which is mapped to this representable map. And because M is a model of identity types, we have a homotopic commutative square like this. So we want to lift these morphisms to the morphisms in X. And this is possible because first of all, UX, we choose UX to be vibrant. So in that case, any morphism is represented by a single morphism in the model category. And we also then, because we choose DX to be a vibration, we can also, lift the reflexivity in such a way that the square strictly commute. Okay. And we want to a similar thing for path induction operation. So recall that path induction is a kind of solution to a lifting problem. So
just so you know, you're a little bit over time, so you should try to wrap it up.
Okay, all right. Let me see. Yeah, so the situation is like this. We have some type A and reflexivity. And we construct this lifting problem. We want to fill in, find some diagonal filler like this. And because M is a model of intensional identity types, we have a homotopy diagonal filler in the localization. Then, because the X is a vibration, we can lift this diagonal filler. But in this case, the upper triangle is only commutative up to homotopy. But in this case, it can be made strict because the reflexivity constructor is a co-vibration. Precisely, it is a monomorphism, and monomorphisms are co-vibrations. So we can make it strict, so it works. But this is not I think this is not a so good way because it is not easy to generalize this split replacement to other type constructors. So here we crucially use this that reflexivity constructor is a co-vibration for a trivial reason. Namely, reflexivity is a factorization of a diagonal map, so it is automatically a monomorphism in one category, and then it is a co-vibration. But we cannot generalize this argument for general inductive types. Yeah, because constructors are not necessarily monomorphisms. Okay, to make remarks. So for that reason, we expect the other approach, namely rewriting or normalization, will be suitable for generalization purpose. Okay, okay, so to summarize, we have introduced a higher dimensional generalization of type theories called infinity type theories, and gave a unified formulation of internal language conjectures, and and actually proved the special case for it, namely the internal. We proved the Kapulkin and Lumsdaine's internal language conjecture for finitely complete infinity categories, and the central technique was a coherence theorem via split replacement. And but future work would be to find, for instance, better split replacement, or we may look at another approach. Also, we are curious about any syntax for infinity type theories. We are not sure, and maybe we can use infinity type theory for some other things, say conservativity. And that is, well, yeah, there's so conservativity is involved with expressed by multi-equivalence between type theories, which is formulated as a Killen equivalence between the semi-model structures. But such a Killen equivalence essentially expressed that the equivalence between the localizations. So maybe it is useful to work in the, maybe it is useful, maybe it is convenient to work in the infinity type theoretic setting, but maybe, I don't know. But this is, I think this is a possible application of infinity type theories. Okay, so yeah, thank you very much. This is end of my talk.
Okay, thank you. Let's all applaud with our microphones muted, visual applause, or with emojis and whatever those reactions. Okay, that was great. Are there, well, I know there are questions because I've seen a couple at in the chat. So please go ahead and ask your questions. Do I have to cold call someone?
I mean, I can start as usual, maybe. First of all, thank you very much. I mean, this looks very interesting. I got two things to say. And the one is, it seems to me, I mean, from what I understand, it seems to be closely related to this conservativity question, right? I mean, so if you look at this, you talk about E infinity, but what about E out the infinity? So then it seems to be just the old question, how to compare intensional and extensional type theory, right? And this was this conservativity question, which was also answered by Martin Hoffmann, right? And it seems to me that what you're doing, in a way, in my view, in my understanding, is the sort of infinity version of this sort of, I mean, compare the infinitary version of extensional type with the intensional one, right?
Yeah, right. In some sense, we are comparing where infinity.
Yeah, I mean,
maybe this.
Between I infinity and E infinity. I mean, that's, I think, the interesting thing, right? I mean,
we are mainly interested in comparison between I and E infinity.
Yeah.
But this, but comparison between I infinity and E infinity are, well, more or less trivial. In that case, because in fact, this is models of infinity is a reflective subcategory of I infinity, models of I infinity, and
so right, you need to start with the one categorical version to
Yeah, I think in this context, what is really interesting is the comparison of one type theory and the infinity
Sure.
extensional infinity type theory.
So so I have another question. So I suspect your development is not constructive, or am I?
No, not constructive.
Yeah.
Well, yeah, we are relying on the theory of infinity category. We are relying on infinity category theory, and it's fun. It's not constructive at all right now.
But can this be fixed?
Hmm?
Can
Well,
this be fixed?
I don't know. It depends on how constructive infinity category theory is.
Well, it seems to me that I mean, you mentioned this sort of more sort of syntactic approach then would work. I mean, not have these problems, no.
Maybe it's let me see, but well, I'm not sure. Well, because we are already using the infinity category theory to define the infinity category of finitely complete infinity categories. Or I don't know how.
Yeah, but I mean, maybe it's just laziness that it's not constructive. Right? I mean, is there a good reason that this is not constructive? It's just.
Just. Yeah. Well. Sorry, but anyway, I'm not sure about the
Sure.
constructivity of this approach. Yeah. At all.
Okay. Thank you.
Okay. Someone else have a question?
Well, if no one else has anything, I did have a small question during the talk, but I think it was cleared up. But maybe you can just confirm that it was cleared up correctly. I didn't remember the definition of the type theory I. Was that with identity types with propositional computation rule for the eliminator, or with a judgmental computation rule? And not I infinity, but I, the original I.
Original
Yes.
I. I'm thinking of a definitional computation rule.
Okay, but then why does it happen that when you truncate I infinity, you get I and not I with a propositional computation rule?
Because, well, the computational rule for I infinity is a homotopy in this infinity category, right? But it is not represented by the identity type. So
okay, got it.
Yeah,
okay,
homotopy becomes strict equality when truncated. Okay.
Yes, I see. So, do you think that you could do the same thing with the with another version of I that had a propositional computation rule? And could you use the infinity type theories to compare the two versions of I, one with judgmental and one with definitional, propositional and judgmental computation rules?
Let me see. So if we start, if we modify I by a propositional identity types, then we can let me see. But in this case, we also have to modify I infinity to be with a propositional identity types, because there is no way to send. Sorry, maybe it's okay. Yeah, but it's more natural to consider infinity version of propositional identity types. And in that case, I think the proof is much simpler, I think. because in the proof of the coherence theorem, we don't have to care about any strict equality. So maybe it's, yeah, I'm not sure, but I guess I guess in that sense, I guess the intentional one type theory with propositional identity types also are also internal languages for finitely complete infinity categories. I guess.
Oh, that's great. Yeah, no, that'd be really nice. It'd be another approach than Raphael's.
Yeah, if it works, then if it works, intentional, proportional identity types are in some sense equivalent to the usual identity types, right?
Okay, are there more questions? Okay, if not, then we will thank Taichi again. And I'll just remind you that was the last talk of 2021, the last talk in the hottest seminar, but that's all that really matters. And we will continue in January on the 13th with the event for junior researchers. Hope to see you there.